Hello. In this video lecture, we're going to look a little bit more at electric potential and what happens around specific charges and how it relates to the electric field. So here I have electric potential is the electric potential energy at 1 point per charge. And we have the force, the electric force due to two charges or any charge is depends on Coulomb's constant, both charges, and the distance between the two of them. And we have the idea that the electric field is related to the force and that charge. Really, what we get from the electric field is that a single charge Q will produce some electric field where other charges, when placed there, will feel a force around it. And since let's make this a positive charge here. So we're just going to say positive. And the electric field lines that we draw go outward from it. So we have some electric field lines that go out in all directions. They're always perpendicular to the surface right here. I probably should have drawn them so they're touching the surface, but I'm not going to go back and do that again. And since this is a positive charge, just kind of made it up there. Probably better off putting the idea that it's positive right there in the middle. There it is, positive, all the charge moves away. Now, at any point away from this charge, there's some potential energy. So let's just say right here, at this distance, we'll call this R. There's some force applied right there. There is some electric potential energy. Excuse me. There's some electric potential energy at that point. And if we're only looking at this charge and within a system, this is the only charge, at that same distance R, all the way around, it's going to have the same potential energy at every point. So if I take this distance R, here, 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 and back over there. At all of these points around the charge, there is the same amount of electric potential energy at that position, or electric potential at that position, if we were to include like some point charge. This is what we'll call equipotential. I'm going to write that bigger. Alright, so now that I have this written up a little bit bigger, we have the same potential based on the distance from this charge, the same electric potential energy at each one of these points. And if I go along and connect them, and connect it as if it were a circle, because it's really what it is, and the world's worst circle gets drawn in 4 seconds ago. So anyways, what we have here is what we'll call potential lines or equipotential lines. Now, along this line, the potential energy is all the same. The electric potential energy is always the same along this line. So here we have, let's just give this some value. Let's say this is 30 volts, joules per coulomb, 30 volts right there. So at that point, the electric potential at that point is 30 volts. And somewhere inside of it, you may have another line here, and we could say here that this second line here, it's going to have more potential. You're closer to the charge. So let's just say this one here has 40 volts. This is probably not drawn to scale or anything close to that. So we have some potential, equipotential. There's some potential along these lines. Now, equipotential lines tell us we can use them to determine the force and how much energy is needed to move a charge there. So if we think about it, if I take my charge again, and I have it here, I'm going to need to change the energy by the energy per charge, per this charge, I'm going to need to change it by 10 volts to go there. That change in energy relates to the work done. All right? A couple of things to notice about the potential lines and the force lines and the electric field lines. They're always related. So the electric field lines are always going to be perpendicular to the equipotential line. So if we go along here, this here is perpendicular right along here. This here should be perpendicular right there. The electric field lines, as they move out or into a charge, or depending on the nature of the charge, they're always going to be perpendicular to the equipotential line. You can kind of think of these equipotential lines as a topography map. How hard it is going to be to move a charge from one position to another. So if you think about a map with a hill on it, if you have to push it up a hill, and as you go more positive, you get higher. As it goes up a hill, it's harder to push it. It takes energy to push up. But to go down a hill, to go away, that's kind of releasing energy from that point. So there's that idea that there's a change in energy based on how you're moving a charge, whether you're moving it towards or away, how far away you're moving it, or anything like that. So just think about this idea here with these electric potential lines. And gosh, that looks like a spider web, which is probably not what I really wanted to draw right there, but kind of crazy. So we'll be talking about this more, about how to draw, and just the idea that at every one of these points along here, all along this circle, the electric potential is the same at all of these points. Thank you very much. There are some questions on the website. Make sure to go through and solve those. All right? Thank you very much again. Have a good night.